Let me make sure. Students who are online, can you hear me? Just type it in the chat if you can, because like it has happened before that. Okay, thank you, George. Thank you, Trevor. All right, so today's lecture is about, it's a gentle introduction to natural language processing, that's NLP. And usually what happens in machine learning classes is that usually NLP is introduced towards the end. But I figured that now we understand recurrent neural networks. Of course, like we can go back and forth and try understanding them better. But now I think we are in a position, and the fact that we understand feed-forward networks, I think we are in a position to understand how word embeddings work at least. There's going to be another lecture following this one in which we'll go into the details. For today, despite the fact that we are like in the just lecture 8, but still, I think we are in a good position to understand word embeddings. So that's what I'm going to do today. Today is an introduction to natural language processing. And if we think about this like as a great larger area of research and of application, natural language processing is actually at the intersection of computer science, machine learning, and linguistics. Because what we are trying to do in natural language processing is that we're trying to find some way to facilitate communication between humans and computers using our own language. So you've seen multiple applications of NLP around you, Amazon's Alexa or Google or Apple Siri, all of them, all of those work on natural language processing, right? So the applications are immense, they're huge. And it's not just that we are like talking to a computer, but in addition to that, we're trying to extract meaningful information from some given text. That's more important, right? Because every information that you see on the web is textual. And so we want to derive important information out of that. That's why we are talking about natural language processing. And two important aspects of any NLP problem are that we are trying to analyze language. And language in itself is complex. And there are so many languages all around, right? So what we try to focus and what we begin with is that there are two aspects of any language, of any text. And the first one is the syntactic analysis. So there is some grammar, there are some rules to every language, right? So if you think in terms of like programming, there is some syntax when you write code, right? So it's similar to that. Any language, be it English or be it any other language, they have some rules, and that's known as grammar. So one aspect of natural language processing is the syntactic analysis, like making sure that grammatically a sentence is correct or not, whether it's following all the rules or not. And believe it or not, that's not the bigger challenge. That can be done, and that is being done quite efficiently. The other important aspect of NLP or natural language processing is the semantic analysis. So we saw a little bit of that when we talked about recurrent neural networks, and we said that if we are trying to encode words or create embeddings of words using one-hot encoding vectors, then we are missing out some information. So what we were talking about was that there is context in language, and there is some semantics to a particular sentence, which can be perceived like with the same words, with the same set of words, the same sentence can be perceived in two different ways, or like more than two different ways. So that's what semantic analysis is. And the focus of word embeddings in general is the semantic analysis, the semantic side of things. Okay, so of the two, like the syntactic and the semantic, we will be focusing on semantic analysis because word embeddings are created to focus on that. But there are certain algorithms within the word embedding algorithms that are going to take care of the syntactic part as well, because basically we are learning from some user input. We are learning from some data, and that data is usually considered to be syntactically correct. So my algorithm is going to learn from that input. And so it's going to take care of that as well. But as I said, these are the two primary techniques, or like two primary directions in which we can work our way through when we are solving an NLP problem. Okay, so that's syntax, and then this is the semantic side of things. All right, so I wanted to talk about word embeddings today. And the reason being that these are an integral part of any natural language processing application today. So what are these embeddings? First, we'll try to understand and how to create them. And of course, creating them in itself is a very complex task. And so we are going to understand some of the existing word embeddings and how they are created. Okay. So in natural language processing, word embedding is a term that's used for the representation of words, right? And so if you remember, we talked about word representation, and I'm going to go back to slides. And by the way, I'm going to post these slides, like the ink slides as well, on Submity. So because I wanted to write more today, that's why I decided to. All right. So let's talk about like what we thought of word embeddings. So we were representing words with some vectors, and they were one hot encoded vectors, right? So let me just like remind you that let's say I have like multiple words. Right. Okay, so let's say I have some word like table, I don't know, chair, man, apple, and so on, right? So obviously any neural network requires some input from your text. And so let's say this is your text. And so you're going to create these one hot encoded vectors. So imagine that your vocabulary, which I'm denoting by V, is of size, let's say 10,000. Usually that's the usual size of a typical vocabulary in a language. So let's say I have that, and so I'm going to create size 10,000 vectors for every word, wherein, like, for example, table is, so it's going to be 0 for all, every element is going to have a position. So every word is going to have a position in the vocabulary, right? And then let's say table is 1 here, and then the rest of them are zeros, and so on. And similar to that, I'll have like some position, let's say chair, and then the rest of them are going to be zeros. And similar to that, I'll have somewhere here. And then for Apple, I don't know, 1, maybe not. So like they shouldn't match. So maybe 0 and 1 here or something like that, right? So every word is going to have a unique position is what I'm saying. For example, table is like 1, maybe somewhere down here, right? Which is different from chair. And so this is how we differentiate between different words in a typical vocabulary. So all of this is good. But then what is the issue with this kind of representation? We said that this was good in a recurrent neural network, right? And that's how we were using the inputs. And then we figured that this is not capturing the context, but still we kept using these as inputs. Now, the issue is for cases like when you go and search on Google and you're typing a sentence, it usually prompts you with the next words, right? And so the way it gets those next words is from some context that you already typed in, right? And so, for example, if I'm saying like, give me apple, and then I'm still typing, so maybe it's going to come up with like, give me apple juice, right? But then the point is that if I'm using like, if let's say I have some application in which I'm using like these one hot encoded vectors as inputs, and the way like visualize these vectors in your feature space. So the way we are differentiating between these words, if you visualize them in your feature space, is that there is some distance between every vector. That's how we're differentiating, but like with in between all of these, right? And usually the way we kind of create a relationship is like we're finding those dot products between vectors and say, okay, this is the distance between this and so on, right? So we think about like if I find a dot product between table and chair, that is going to result in like a 0 because they have like different positions, right? So in some ways, of course, like table and chair exist as vectors in that space, but it's difficult to find a relationship between them. So basically, if I keep using this kind of a representation, that nobody's stopping me from like give me apple chair. Maybe chair was equidistant from apple as much as juice was. And so I picked up chair, right? So the point I'm trying to make here is that we cannot have these kind of representations of words in like as some independent entities. There is some relationship, and we obviously discussed that when we were discussing recurrent neural networks, right? So now we're going a step further, and let's say I'm like creating this kind of an application where I have some words given to me, right? And I'm trying to find the context, and also I'm trying to find something like if somebody gives me like, give me orange, And so my expectation is that the word that the application is going to give me is going to be, or the word that's going to be predicted is orange juice. So there is another aspect apart from the context that we talked about. Think about it. If you look at both these sentences, give me apple juice and give me orange juice, here I'm also implying in some ways that this apple and orange are also related in some ways. And so basically words that are similar to one another might be closer to certain words. For example, both apple and orange should be closer to juice. Right. So another aspect apart from context is that how related are these two words? And using this one hot encoded way of representing these words, there is no way that I can bring these two closer, because apple is just like apple, and then maybe orange is some, I don't know, something like this somewhere, right? And so it's hard to explicitly make them closer to one another. Although I know that there are certain features or there are certain attributes of this word that make them really close to one another, right? So for that particular aspect of language, wherein you have certain words that share certain properties, and so they're closer as compared to words that don't share those properties. And based on that, we can predict like the next word, or maybe we can predict certain outcomes, or maybe we can predict context. And so that's the motivating idea behind why we need word embeddings. And so what exactly are those? So let's actually see what these are. Okay. So I'm going to like write a few words here. Let's say man and king, apple, orange, I don't know, queen. All right. Instead of writing these words as one hot encoded vectors, I can come up with new features, right, that somehow make some relationship between these words. Okay, so what could those be? For example, let's say I have a new feature defined that's known as gender, right? And the way I describe this gender is that, let's say it takes values from -1 to 1, so -1 for man and 1 for woman, right? And so what will happen here is that if I've created this new feature gender, then I'll have like, let's say -1, -1, +1, right? And apple, orange do not have gender, right? So maybe 0 or like, I don't know, 0.00 something, a very small value basically for that, right? And we'll come to we'll discuss, like most part of today's lecture is around like how do we get those values. But for now, just understand that I'm creating new features to identify these words, right? Because I just figured that one hot encoding is not enough for a lot of applications. So let's say gender, and then maybe age. Man has age, right? So maybe it has some value, I don't know, 0.8, 0.85, and then 0.85 again. And then I don't know if this is going to have like some small value for that, maybe, I don't know, right? So similar to that, I can have another attribute, food, and then along this attribute or feature, right? Man most likely will have like 0, right? And then king also 0, but apple, yeah, 0.99, orange maybe 0.99 or 1, and then almost 0 or very negligible value, right? So similar to that, I can go ahead and create more features that are specific to these words, that somehow describe these words, because that's how like we learn language, right? As kids, like we were told that this word means, it is associated with certain other things, right? And so it's like very similar to that. We are doing this kind of a like feature creation. Okay, so in the language of natural language processing, these vectors that we will eventually create, right? So these vectors are my word embeddings, because for every word, for example, man, of course, I created a new vector similar to the one hot encoded vector, maybe different size, because maybe usual size for this one, for like, as we'll see for the Word2Vec, is like 300 something, 300K or something, usually 300, not K, 300. And so the point is that, of course, we still have a lot of elements in that vector, but we have a better way of like defining that particular word. So for example, when I'm going to like use these as representations for these words, and I let's say write give me apple, and then it's going to prompt juice, depending on like how close apple is with juice. And similar to that, if I say give me orange, chances are high that it's going to give me juice, because apple and orange will be like very close to one another. So if you look at the values that they're taking up, the attributes they're taking up are very similar to one another, right? So word embeddings are nothing but a way of representing or better representing every word. And in addition to just like their own standalone representation, we also have some ways of finding similarities between words, which is definitely a better representation as compared to um, what we had earlier. So this will have a better generalization when we're using text or when we're using language and trying to predict a word given some context. Now, of course, the big question remains that how do we get these values? Like just now, I just populated that word, right? And a quick answer to that question is that we are going to use a neural network to generate those. Okay, that's bad news, right? Whenever neural networks come in, backpropagation comes in and gradient descent comes in. But yeah, we'll have to deal with that. But that's how we get those values. And after we get those values, things become really easy for us. And the good news here is that these embeddings, or so-called these word embeddings, are created with a pretty shallow network. So you don't need deep networks in this, as we'll see today. Okay, I think I saw a question pop up and it disappears on my screen. Sean, okay, so your question is, since they are both close to each other, they both have to be close to juice. So not necessarily. The point I'm trying to make is that this juice is usually associated with apple, right? And then with fruits, right? And so the attributes of juice will be such that this juice will already be close to both of them, or to other fruits, right? Because I would have learned this information from some text. And so obviously I'm assuming that apple and orange are fruits, and they are, right, as far as like my knowledge goes. And so based on that information, when I'm typing this, because there is a relationship between apple and orange, there is a relationship of both of them with juice. Okay. All right. Other questions? Yes. Yes. That's an excellent question. And there is a whole, so the question is for people who are online, that how do we go from this bigger feature space of like 10K to this 300? And the way we do that is using a neural network. So I'm going to. Yeah, so that's the good thing about this. You don't need to go back. You don't need to go back, yeah. Because like everything, your entire vocabulary will be in this like low dimensional space. Usually this is low dimensional. And then you make predictions right then and there. So you don't have to go back. That's a good thing. Unlike what we say in like, I don't know, in other feature reduction techniques, we don't have to go back. As you'll see when we create embeddings for Word2Vec. Just like high level, just think about this feature space, this new feature space. You have a good way of representing man, right? And so you can just like stay there and make predictions because you also have juice in that feature space. So you can make predictions within there. So you don't need to go back. Does that make sense? Yeah, and we'll see how specifically we make that transition. We'll see. So that's the whole point of today's lecture. Like, how do we make that transition? Okay. Yeah. Other questions? All right. So moving on, and before like we move on with the slides, I just wanted to show you something. I don't know how to escape from the slideshow. This one. How do you go out of this? End slideshow, maybe. Okay, I'm going to come to the properties of these embeddings in a second, but if you go back to the lecture notes, the Google Colab that we have, the first thing that comes to your mind is like how this visualization, that's like, I think that your question is coming from. And so there are ways of like visualizing this. Think about it that you had some high dimensional data in high dimensional space, obviously, because you have like 10,000 words in a vocabulary and then one hot encoded vector for every word. So it was hard to visualize. And the like one of the bigger challenges is like for any machine learning practitioner is that we want to visualize, we want to see. like what's going on. And so there are techniques, and I've just like listed two of them. There are techniques like using which you can visualize your new, I would say, data that you've created. And like one quick way of thinking about it is that it'll come down to, let's say you're coming from a high dimensional space, and this is what this one does, this t-distributed stochastic nearest neighbor embedding. So it's going to bring those new embeddings for every word. Like it's going to calculate the distance between them, and that's going to bring them down to a lower dimensional space where you can visualize them. So for example, like let's say we were able to come down to a two-dimensional space. So you will have like man and maybe like king pretty close to one another. And then you can like see, I don't know, woman and queen pretty close to one another, because based on their attributes, they were closer. And so you can actually visualize in a low dimensional space that they are closer, and then that's how you are like making your predictions. So there are techniques that you can check. One is like this PCA, and the good thing is that if you go to this link that's provided by TensorFlow, you can visualize some of the existing embeddings there. I'll just quickly go there. And by the way, we're going to look at like what this Word2Vec is here, right? Word2Vec is like a technique of creating these embeddings. And so we're going to discuss that. But here it has like these different options of like, how do you want to visualize these? TSNE is like one way of what TSNE algorithm does is that it creates this low dimensional space by combining together vectors that were really near, like close to one another in the higher dimensional space. So it's going to just like let you visualize that. So this is something that you can go and just explore on your own and like see what happens if you're using a different technique or a different algorithm to visualize this data. But yeah, I know that this question comes in multiple, like whenever I talk about NLP. And so this is a good embedding projector, projector.tensorflow.org is a good way of like visualizing these embeddings. And yeah, so I've provided a link here. Whenever you have time, you can go back and look at these. Okay. So having said that, and I would definitely close this because, okay, it won't let me close this, so that's fine. Okay, so now we need to understand some of the important properties of these embeddings, because that is going to help us understand how these embeddings have been generated. Like what really happens when I've created these new vectors with certain new features, right? So let's try to understand that. And I need to write on my slides. Okay, so what like the important aspect of these embeddings is that it is like a vector as such, right? And then there is this like new vector space where we can imagine that each of our vectors exist, right? And so if you think about like the properties of vectors, you can find similarity based on the distance between the two vectors, right? So for example, cosine similarity can help us get or understand the like how similar two words are, right? Based on their values. So for example, I'm going to go to this like very famous example that gives us an idea of like how this vector space is actually creating this like these semantics between different words. So this is a very famous analogy, and you will find it in like almost every natural language processing tutorial or paper. Is that let's say the problem that I'm trying to solve is the way man is to woman, right? Then can we say something about like king is to what, right? Using these like new features or using these embeddings, can we do something about it? So, well, a quick answer to that question is that, remember the way we created our embedding. So obviously we'll have like some kind of new feature, right? So man, woman, king, queen, let me write it in short. And then maybe you'll have things like gender, age, royal, and so on, right? Other features. And then these will have some values, right? So for example, this and this, and then some values for, I don't know, age, how important the age was, 0.01, 0.2, and so on. Like, I don't know, this is like high, this is going to be high, this is going to be low, high, low, right? No, this is going to be, yeah. And I'm just like making these numbers up, so it doesn't really mean a lot. But basically what I'm trying to say is that each of these is a vector, right? And if we imagine this new space of my embeddings, right? So I'll have like a vector for man, right? And let me draw it. Can I draw it somewhere? Okay, I don't think I'll have space here. Let me draw it in a two-dimensional space. Let's say I'm able to visualize these in two-dimensional space, right? And so I'll have like man here, right? And then king here, because based on their genders, they must be like closer to one another. And then we'll have woman here, right? And then queen here. And we can, in some ways, if we have like this vector that joins them, right? Or this, right? We can draw some relationship between these vectors. But most likely, what has been found in most experiments is that these are mostly parallel, right? So in other words, what I can say is that like the vector for man minus the vector for a woman is almost equal to this, the same thing, like king minus b queen. Okay, from basic vector knowledge, we know that, right? And this relationship is not because we created something, but because of the way these embeddings were created. They were created based on certain properties, and so obviously they will hold this kind of a relationship, right? So now, usually, like if we are looking at a problem like this, like some relationships between words, right? The relationship that will exist is that I know, like, let's say the V for man and the V for woman and king. So I can find that the missing word is that vector, which is creating this relationship. So most likely the vector for queen, right? So this is like, because this relationship exists, basically in this new embedding space or in this new vector space, the problem that we are trying to solve is something like this. And let me go to the next slide. Okay, so the problem that we are trying to solve is this one. So I have like for any word W, I'm trying to find the word, the similarity between this like word, let's say whatever that missing word is, and this king minus man plus woman, right? And this analogy can be drawn for any other word as well, right? So basically what I'm trying to do is I'm trying to find this word that maximizes the similarity, right? If you imagine that parallelogram, those two vectors, right? And what could be this like this similarity function? This is just some function for similarity. So from our knowledge of vectors, we know it could be cosine similarity because that's the most obvious choice for any similarity-based function. So basically, if you have like two, if you remember from your vector calculus or generally from vectors, is that the cosine similarity between any two vectors is going to be the dot over this. And so I can use this function here to find the similarity and find that missing word, that using which we can draw analogies, right? Or like if you're not interested in cosine similarity for some reason, in some applications, Euclidean distance can also be used. Because basically all I'm trying to, like the point that I'm trying to make here is that if you visualize those embeddings in that new vector space, the relationship between every pair of words is somehow related to the relationship between other two pairs. And that's what was quite evident in this picture here, is that, like, for example, the relationship between man and woman and king and queen is like parallel because they have some certain shared attributes. And this, by the way, and this, I'm not like making this up, and I will just go and show you the research paper that actually proved this, and where they're showing that the same relationship can be extended to any other problem. For example, let's say finding the capitals of countries. So, like, for example, I can find the capital of United States, and based on that relationship between USA and Washington, D.C., I can find the relationship between any other country and their capital, right? So let me show you that, because I want everybody to read that paper at least. And yeah, by the way, I've pointed links to many different research papers, and I haven't pointed you to so many papers before. Reason being that NLP is a pretty active area of research, and like many important papers have come up in the last decade or so. And these are some like groundbreaking, I would say, research papers that you should be aware of, because like many of the products that we're using in NLP have come out of these research papers, right? So let me quickly show you which one I'm talking about. Okay, yeah, here. So they illustrate using the same idea that, for example, man is to woman, uncle is to aunt, and king is to queen. And so how you can create a parallelogram and find the missing one vector, right? And so this is like from basic vector calculus and basic vector algebra, right? So here they're showing that using this exact same technique, I think they have more experiments. Okay, that was the other, I think this is Mikolov's paper, right? Yeah. So yeah, and wherever you see that name, that's like an important researcher in NLP. So yeah, so this paper actually talks about like how can we come about saying that we are actually in this new embedded space. We are looking at the difference in these two vectors and then trying to find one missing piece in that entire relation. Okay. All right. So that was like high level idea of like what are some of the properties of these embeddings or what are these embeddings? But now comes the important question. Where do we get these embeddings from? Right? I'm just like making up these numbers until now. And this paper, of course, talks about a little bit about that. And I'm going to go back to our notes and talk about here. Okay, so what are language models? Well, language models are any machine learning model that is trying to create a relationship between our language, text, and some kind of prediction, generally speaking, right? So high level, anything that involves language is a language model. But we are specifically interested in word embedding types of models, right? So it's like a sub section or subclass of those like language models. And the quality of language models is based on their ability to learn a probability distribution of like words in a dictionary. Because if you think about even the embedding values, right, we are trying to come up with some sort of like conditional probability, like based on these words, what is going to be the next word, right? So what is the probability of finding this one? And so that's a high level idea of like how language models usually work, right? Because that's what we are trying to predict. And yeah, and most of the applications as well. Oh, that's okay. Did something break? Oh, okay. Okay, so in most of the applications also, we are trying to predict the next sequence of words, right? Or sometimes doing sentiment analysis. But regardless, we are trying to come closer to the probability of getting some output word, right? And so that's why we are interested in these embeddings and how to compute them, right? How to compute the values. And so there are two methods to compute word embeddings. The first one is like count-based methods, and the second ones are the predictive methods. We're not going too much into the count-based methods. Of course, like one of the embeddings today that we're going to cover is based somewhat on count-based methods, but we're focusing more on predictive models that try to predict a word from maybe its neighbors or maybe from the entire information that I have for that word and so on, right? So in specific, the word embeddings that we'll try to understand how to create are related to this model, which is the Word2Vec model created by Google, I think, the last decade or so. And it's nothing but a shallow two-layered neural network, which is trained to reconstruct the context of words, right? So you will see that word a lot when you start like working, if you start reading papers, if you start working with natural language processing, you will see that word a lot. And the high level idea is that word vectors, again, the way we talked about the properties of embeddings, right? So the high level idea is similar, like you have word vectors that are placed in vector space that share common context. And our goal is to get those vectors, to learn those vectors from my input data, right? And so that's exactly what Word2Vec does. It's computationally efficient, and it's like it predicts using like some context, maybe it predicts some word, or in some cases, instead of predicting one word, it predicts a lot of words that have probabilities associated with them. And the probabilities describe how close is this output word to my input. Let's say I have a single input word, right? So that's my context. And then there is some target that I'm trying to achieve, right? So for example, let's say hot coffee. So if hot is my input, then I'll have like coffee, tea, and like words that are associated with that. And then there is a probability that is going to be associated with like coffee, tea, and so on, right? So that's what this is going to predict, the probabilities. And the one that has the highest probability is the one that I'm going to pick up, right? So there are essentially two variations of Word2Vec, as I'm like shown here. If for some reason doesn't like this pen. Anyways, yeah. So yeah, the first one is this continuous bag of words, continuous bag of words, CBOW model. And the second one is the Skipgram model. So what I've decided to do today is like go into the details of Skipgram model, because this continuous bag of words model is just like a flipped version of my Skipgram model. Right, so these are the two different variations of Word2Vec embeddings. All right, so let's look at like high level what these Word2Vec embeddings are. Okay, here. Now, what happens is that I have an input vector, which is like a one hot encoded vector. And remember, I have to learn those embeddings or those values for that word, right? That's what I've decided to do, right? So high level, the way this creates this Word2Vec, high level, the way it creates these embeddings is that I'll have a shallow neural network, right? By shallow, I mean maybe just like a single hidden layer, right? And when I input some word, let's say like this one word, right? And then what I'm going to do is I want to, I'll have like some weights on these input edges, because this is a computational graph, right? And then I'll have like these hidden layer neural like neurons. Well, it's just like a simple feed forward network. And then finally, I'll have an output layer, right? This output layer is usually a softmax. The softmax, remember, gives out, it's slightly different from the binary logistic regression model that we've used, in the sense that logistic regression just gives out, like the sigmoid gives out only two outcomes, right? 0 and 1. Sigmoid can give out as many outcomes as you want, because the way the sigmoid is like defined is this summation of all x's of all inputs from like 1 to n or whatever. So if you have n inputs, let's say, you will have one output for each of these n's. And so basically a probability associated with every word in your dictionary. So again, let me repeat, high level idea. If you remember the high level idea, then when we go into the details of the Skipgram model, you will be able to relate to that. So the high level idea is I'll have an input vector for, let's say, a word, right? So some context word, right? And I'm trying to predict what is that word that's like very closely associated with this one word. So in order to do that, what I'm going to do is I'm going to input this, right? And have some initialized weights here, and then do some computation here, maybe a sigmoid, maybe just like a summation, depending on like how I'm trying to learn from this data. And then finally, I'll have an output layer that's a softmax classifier. Softmax does nothing but calculates probability for every word, right? So let's say this word was hot, and like here you'll have some probability value for coffee, and you'll also have some probability value for tea, right? And most likely, depending on the inputs that I've given this neural network, and it has learned from that, most likely for hot, it's going to have like a higher value for like coffee or tea. That's my assumption based on the, because obviously I'm getting this some text from somewhere, right? So this is like the high level idea of like how these embeddings are created. So now the question arises, where are those embeddings, right? Because I'm like really interested in like getting those embeddings. So in most situations, in most cases, these are the embeddings for that word. So for every word, I have some weights, and those weights essentially are my, the weights of this like hidden layer are my embeddings. Right? So of course, this is a task where I was trying to predict the next word or the most closely associated word. But for this word, this hot word, I'll have some embeddings, right? I need like that new vector of 300, size 300, remember? So that is going to come from these weights. And of course, the entire process is still there, in which I'll have, let's say, these weights, I'll have them initialized, I'll train this network for a certain number of times, I'll have the back propagation, and the back propagation is going to update these like values in my weight matrix. And that weight matrix is going to give me my embeddings. Okay, I'm going to go into the details of like how this is structured specifically in terms of like the dimensions of each of these vectors in the Skipgram model. But as long as you understand this high level, I think we are okay, right? I'm going to go into the details, of course. Okay, so this is how high level we generate those embeddings that we've been talking about in any Word2Vec model. All right, so moving on. In addition, so if you remember this like property of like king is to queen, man is to woman, right? So that is captured when we start learning with that shallow network, the shallow neural network. And because those relationships between vectors exist, and so we are able to generate other similar relationships as well. Because just imagine that you're learning and you're generating those embedding vectors for every word, and because you're learning from the same data, so the relationship between man, woman, king, queen, the analogies are by themselves being learned from that data or from that text. So that's the good thing about these embeddings, because like these relationships exist in those embedded vectors, and I will be able to use them to answer certain questions or maybe get the next word and so on. All right. So how does these, and I think I had, okay, so I think I have done some like wrong sequence of slides. So this like training algorithm part will come a little later. So I'm going to skip this one and I'm going to rearrange them. But I wanted to show you this, right? So we talked about the Word2Vec model just now, right? And I said that there are two variations. Just remember there are two important variations of Word2Vec. One is the continuous bag of words model, and the other one is the Skipgram model. And if you just look at the structure, just like forget about the embeddings and everything. If you just look at the structure, you can see that these are pretty much like flipped in the way we are trying to like use them. So basically this continuous bag of word model, it is given some context. That means let's say a certain number of words, right? And it's trying to predict maybe the next word or the middle word or something like that, right? So it's like it has multiple inputs and just one output. But in the Skipgram model, we have one context word, right? Let's say, as I said, let's say hot or coffee, right? And then I'm trying to predict the probabilities of all other words in my dictionary and how closely are they related to this particular word. So basically, I'm trying to predict like the probabilities of all other words. So that's the fundamental difference between these two. We are going to look at like how the Skipgram actually learns and how this works in a greater amount of detail. But I've provided the paper from which I've derived all this material. So there are two papers, and I'm going to quickly skim through them. And that talks about this continuous bag of words model as well. So if you understand like Skipgram, that's pretty much the same thing. Just like the objective is slightly different. Okay, let me see if I can go to that paper. Okay, so this is the one that talks about how can we create in general neural probabilistic language models. Again, this is a very well-known paper. If you've come across this word Benjio, you know that this is an important NLP related research paper that talks about how can we use like neural networks to create these embeddings and how what problem exactly are we trying to solve. So in general, for any language model, we are trying to predict the probability of a certain word appearing given the rest of the words. And usually the language model has like, sometimes it has this assumption that they are independent, sometimes it does not have. And based on that, we have to tweak our model, right? So this is, I think, one of the first paper that talks about how can we create those embeddings that I just talked about. Right? So this is one. And then even more to that, I think, is paper number. Yeah, so this is the important paper that actually came from Google, and this was the one that actually talked about what this Word2Vec is. So this talks about this introduced Word2Vec. It's a very famous. I think, like, if you go and look at the number of citations for this paper, it's like huge on Google Scholar, right? So this is the paper that introduced what Word2Vec embeddings are and how to create them. And so it talks about both the Skipgram model and the continuous bag of word model, but it goes into the details of like the Skipgram model. And so that's why I just picked up all this information. I'm going to talk about that in today's lecture, right? But regardless, it makes sense to read this paper, given that it also talks about techniques of training your network and how to improve the overall training process. So I'm going to talk about that anyways, but I still provided the link from where I got all this information, just in case you were thinking that I made up that information. So, okay, so going back to the Skipgram model, and what it does is that, let's say I have a sentence. So basically, if you remember the picture of the Skipgram model, let's go back. Right, so you are given some context and you're supposed to maybe within some window, like let's say, and I decide what size window, let's say size 4 window. That means 4 words ahead, 4 words behind. I'm trying to predict what all words could appear in that window or in that range. Okay, so let's see what can be done. And I'm also assuming that I have like a bigger, like a longer sentence. So for example, I have, okay, what happened? Okay, so I'm assuming I have like, I want a hot coffee, and then maybe make it bigger with my cereal bowl. And so what my goal is that I have a context that's given to me, usually denoted by C, right? That's hot. And I have a target, usually denoted by T, right? And this is like a supervised learning problem in the sense that within, let's say, a window of 10 plus minus 10 or plus minus 5, I'm trying to predict what all words can be there in that sentence, right? So that is my target. So let's say if my target is coffee, then that's good. But then my target could also be cup. Sorry, not cup, because we don't have a hot cup. Maybe, okay, I want a hot cup of coffee. Maybe let me make it, all right? So I can say I want could be a target, right? So all of those. So basically what I'm trying to do here, like with these examples, this is not important like what words are coming up here and what sentence I'm looking at. The point that I'm trying to make is that I'm trying to create a mapping between like my context and my target, right? And the input is going to be the sentence. And then basically I should be able to like create some kind of a mapping. And so how do I do that, right? How do I do that? And in like, if we think about this mapping, this has to do with the similarity between words, because that's what an embedding was. And so that's what I'm trying to do in a Skipgram's model. Now, going back to the English, so how is this model created, how the Skipgram works, is that I have this vocabulary, like English language vocabulary of size 10,000. That's the usual size that we use, right? And what I want to do is I want to have like some kind of an embedding vector for this, like, and I'm denoting this embedding vector by E, right? So I want that embedding vector such that when I like pass it through this softmax, I'm able to get some probability value for these target words, for each of these target words, right? This is like high level idea. So basically when we are passing it through the softmax, what we are saying is probability of getting the target given the context, right? And that is given by, and I'm rewriting the softmax, will have like all the weights of the weights of the edges that are coming into my output layer, right? And usually transpose times the E of the context, and then the summation of the entire 10,000 words. And again, like let's say this is J is from 1 to 1,000, 10,000, and then E sub C. Oops. Yeah. Okay. So again, for this neural network, similar to what we've seen before, because I'm trying to predict here this y hat, which is nothing like a probability value or p hat, the loss is again the same. We have seen that before. So the loss is going to be the difference between y and y hat, and it's the log loss transform again, because if you think about it, the softmax is pretty much similar to my logistic regression, except that instead of like 2 values, I'm getting more than 2, like n values, depending on like the number of words I have, right? So I'll have minus the summation of i's from 1 to 10,000, yi log predicted yi. Is the exact same equation that we've seen in logistic regression, with the exception that my summation will have like these 10,000 values, right? So this is high level of how the skipgram works, but now we need to go into the details of like what exactly is the input, then how do we generate it, like generate the weights, and then what happens in the hidden layer, and then how do I get the outer one, right? So all of that is important, but just quickly, like when we think about the training of this, the thing that must be coming to your mind is that like the size of the vocabulary. And so like every input is size 10,000 or like whatever the size of the vocabulary. Right? And that in itself explains that although this is going to be a shallow neural network, but it will take like a lot of time and it is going to be a slow process. Because the way a neural network, and this is a gradient based network anyway, right? So we will have gradient descent, we'll have back propagation, all of that is going to make the network really slow. And there are ways to improve that. We'll look at those methods as well. And they are provided in the Mikolov paper, if you just want to read them. All right, so let's go into the details of like what exactly is happening, how the input is coming, how the embeddings are created, and what output are we getting. And okay, so going here. Okay. Just wanted to see if I'm missing something. I'll just go and quickly check. Okay, what's this one? Okay, this comes later. Yeah, that's what I wanted to make sure. Okay. So now the good thing about these embeddings is that, as I said, I'm interested in those weights, right? The input weights, the input weight matrices. So high level, if you think about this Word2Vec, and as I mentioned, I think somewhere here, is that it takes like a large input vector, compresses it down to a smaller dense vector, and then instead of like decompressing it back to the original input vector, you output the probabilities of the target words. And the other important thing is that the rows of these hidden like layers here are the weight matrices or the word embeddings that we want. So in some ways, we really like to stop at this hidden value because that actually gives us whatever we wanted, right? And then if we think about like this thing, if we think about the probability values, we may or may not want them because like this is just like a specific application that I'm showing you, that I have a context word and then I want to find the probability of every word that's like related to that context word. But in terms of the embeddings, we are like almost done here at this point. So of course I have the embeddings and I wanted to find the probability of the context words because that was my application. But as far as the embeddings are concerned, the learned weights are my embeddings, just to give you an idea of like what's going on. Okay, let me show you like what I'm talking about. Okay, so let's say I have like a word that's my input. Okay, so I have like some word, right? And my entire vocabulary is size V, right? So this is going to be size V. And so let's say like it's one somewhere, but rest of them are like all zeros. That's my input for that like one word. And that's my C, my context, and I'm trying to predict like some target word. And so what happens is that I'll have like these weight vectors, right? And so this is the first layer, I'm so denoting it by W1. And if you think about this, this is going to be V times N. Now, what is this N? Right? V is my size of the vocabulary, which was 10,000, right? N is the number of hidden nodes, right? And what are these representing if you think about these nodes? What exactly are these representing? Well, these are representing my new features. Remember when I said man, woman, king, and then on the left, I had these new features, age, gender, and other things. And so basically I'm coming down from that 10,000 size space to at least 300 because I just decided that I can have those 300 features and like almost describe every word, right? And so I do come down to like these 300 words, right? So this 300, that's my hidden layer. And so this is like H1. And okay, so what happens here is that I have like this V by N. So if you think about it, I'm coming and I have like these 10,000, and then for each of these 10, like each of those 10,000, I'm multiplying it by this 300 only, right? And then eventually I'll have like these outputs. If there is an output layer and I'm interested in finding the probability, so this is my softmax layer. Here I'll have like, and maybe a better way to denote this is not this, something like these. So basically I'm going to have like all these different. So if you think about like these different boxes, I can write this down. So this is like a score for every word in the vocabulary, right? So in some ways, yes. Yeah, so for the hidden layer, it's usually the sigmoid, and sometimes we just sum them up. So it depends. In most situations, it is the sigmoid. Okay, so here score for, like in many cases, it's tan H as well. If I remember correctly in the paper, it's tan H. Yeah.
100 layers.
Okay, it's not depend. So 300 does not come from the number of words. It comes from the number of features that I'm using to describe the words. So the number of words is this V. So for example, V here is going to be 10,000. And then N is going to be 300. Why? Because I decided that there are these 300 features using which I'm describing the words, right? So I've actually come down to a lower dimensional space, which is good in some sense, right? But of course, not as low dimension as I would like. But yeah. That's an excellent question. And so people who are online, the question is that is there a rule of thumb for like the number of nodes in the hidden layer? And the good thing here, as I'm going to talk about it in like today's lecture only, is that this Word2Vec is already created for us, and we can just like pick it up and use it. And it works for most like English language type tasks. It works well. So they've already figured that 300 was the one for like English language, and it works well. But yeah, if you're creating your own embeddings, then it's like it's a trial and error type of a thing. Maybe you can start with 100, or maybe then like move on and see if you're getting some, I would say, improvement or not, right? But then I would say if you're like trying to use any of these embeddings for any of your like projects or in-class homeworks, then just go and pick this up, because this is like pretty like well optimized, and that's what the fundamental idea of transfer learning is. Like they have already generated these embeddings for us, and we just need to pick that up and utilize it for whatever task we are using. But then this is an important question, because for many languages, we don't have such good embeddings available. In fact, I'll point you to this ongoing competition on Kaggle that's talking about generating these word embeddings for different languages. So can we create embeddings for like, can it be language independent? Of course, it's a very hard problem to solve, because each language has their own semantics, they have their own grammar, they have their own way of like expressing things, right? But yeah, that problem exists. So if you're interested in that, you can just like jump onto that competition. That's a very good question. All right, so going back to this, if you think about like the probability values that I'm getting for every word in my vocabulary, actually, this is like very close to getting the probability distribution if I have like input a lot of text here. So I can really get the probability distribution of words in a language, right? Because I can just like keep input, like keep having input of like certain words from a certain sentence, and then creating these probability distributions for every input, right? Which is an extremely useful thing, because like for a certain language, in some sense, I will have some idea of like the relationship between different words and different sentences. So again, that's like extra information. Coming back to what's going on here. So I'll quickly show you a small example. Let's say I have a word, and let's assume my input, my dictionary in some parallel universe has just 3 words, right? And so let's say this word is this, right? Just to make things clear what's happening, right? So this is my 1 times v, which is my input, right? And then what happens is that I multiply it with these weights, right? So these weights are going to be something like this, depending on my input layer n, right? So let's say I have the n here as 4 hidden neurons, right? And let's say like these are the weights. So I just made this up, right? And so these are like, these are multiplied. So for example, this times this, and this is going to give me my hidden layer output, right? And so because there is just like 1 on the second column, and so that is going to be just the second row, right? And so this is going to be like E, F, G, H. This is like precisely what's happening for every word, because every word in my one hot encoded vector will have like a 1 at certain place, right? Using that, I will create some weights, and these are going to be the embeddings for this word, because these are the weights for this word when I did this like dot product. Right? And then eventually I'll create these probabilities that are associated with that word. So those probabilities are also useful, but for like word representation, this thing is enough. That's all we need for like representing this word, if that makes some sense. All right. I think I gave you a lot of information, just like break for 5 minutes, and then because I need to talk about like some efficient algorithms that I use to train this network. People who are online, you can put in your questions in the chat anytime, and like I can go back in the end and check those. Let's get started again. So going back to our discussion of the Skipgram's model, now this makes some sense as to where we are getting the embeddings from, and the fact that, like, let's say I'm trying to create word embeddings for English language. I can just like train it based on some input training set or from like diverse set of inputs, and then create these word embeddings that can be used for certain other tasks. And if you ever come across, and we'll come across those kind of models more often, even in like when we talk about convolutional neural networks and computer vision. And similar to that in language, in natural language processing, we have this Word2Vec model. You can just like pick it up and use it and use the embeddings. Maybe you can improve from there, but they do have this basic set of embeddings created for like, let's say, English language. And the way it has been created is something that I just talked about. And like going forward, the thing about probability distributions, the way this is done. Okay, so I'll have, let's say, this 100, 10,000 words, right? And then I have like some 300 hidden, whatever that is. And so once I've multiplied them, we just saw that you're going to create a vector for every word, and that's going to be its embedding, right? And think of that as like a lookup table for words, right? Of course, you can improve it by training more with new data, but you will have that lookup table there for you, and then you can just use it, right? And in addition to that, one quick thing that I wanted to point out is that there is this like softmax layer as well in Skipgrams that we just saw. And so that has like these outcomes. And this goes back to our basic task of having some context, like, and we're trying to predict some target or something like that, right? So let's say I'll have like this input word, any input word here. And I will have these targets, target 1, target 2, and so on. And this, by the way, is going to be a result of the weight matrix that comes out of this, right? Of this hidden layer. And so there's going to be another weight matrix, which is different from this W1. And why is this important to like understand is because this here will encompass like more relationship amongst the words that we had or amongst the features that we have. So that's going to capture that as well. And so I'm going to get like some probability for this word, some probability for this word, and so on, right? But just like something that I wanted to point out is that there are two weight matrices, this one and this one. Although this is a very shallow network, but this is what's going on in this entire Skipgrams model. Okay, so that was just like more information about the Skipgrams. Yes. Can you say that louder again?
What exactly is the probability?
Yeah, that's a good question. Again, people who are online, the question is like, what is this representing? So this is representing how close, like in comparison to my input word, let's say this was some context, right? How close are these words as compared to this input word, right? So those are the probability values of like probability of getting this value given this context, right? And so as I said, if this was like, let's say the input word was hot, then the probability of getting coffee would be pretty high because usually hot is associated with coffee. And then it like the probability value for ice cream is going to be pretty low because ice cream is not hot, that kind of relationship. So that's why I said that we are getting these probability distributions for all the input words, which is like even more useful if you think about it, because we have created some probabilistic relationship between words. Okay, so that was the Skipgrams model. The other model, the continuous bag of words model, uses a similar idea, but I've left it for you to go and read in the Mikolov paper. And please make sure that you read it because it uses similar logic, but it's just like the way this is set up is kind of flipped in the sense that you will have like multiple words as inputs, but still you're going to put them together through one hidden layer. And the output is not a softmax, but usually like you sum those up. So maybe sometimes you average them or something like that, depending on like what is the application. Usually they're averaged for every word. So basically the application there is that let's say you're given like a set of words, like a sentence, and based on like the previous 4 and the forward 4, you're trying to predict this word. And so that's why you're trying to input these or both of them. Okay. So again, as I said, it's like many of that is like repeated in the Skipgram model. So I'm not going into that, but please quickly go and read through that to understand that how that works. It's just that they're trying to solve two different problems. Okay, so coming back to this, and I have like a better picture of this. So if at all you're confused, this is like a high level, this gives you like how Word2Vec usually works. So this is a more generic way of like denoting that this is like a shallow neural network with a single hidden layer. But then the issue that this network faces is that now you're familiar with gradient descent. In fact, you've implemented gradient descent. And with very simple models and with very simple data, you saw that it could be pretty slow, depending on a lot of factors. We saw that ourselves, right? And now we are talking about a model wherein I'm getting an input of size 10,000 in just like for a single iteration, for a single word. Think about the skipgrams. I'm getting a 10,000 size vector, passing it through that layer, learning the weights, then doing some computation, getting the softmax, and then I get the loss. And then I calculate the gradients, and then I propagate the gradients back, and then make one single update, right? So this points to the fact that this can be pretty slow, pretty inefficient, and we need to do something to make it efficient, right? And so there are two known algorithms that do that. One is known as subsampling, and the other one is known as negative sampling. So let me quickly go here. Yeah, so running, of course, we can say that like Word2Vec has a very shallow net. It's not a deep network, but it's a wide network because the size of the input itself is the size of the vocabulary. And the vocabulary could be like anywhere from 10,000 to 20,000, right? So we need, and of course, you need a huge amount of data to tune the weights as well. You must have figured like what I was showing you was like a single input, a single word, and then all those steps for that one word. And then I need to input like all the data that I have because I need to train it so that I get like really good weights. Because like everything, every NLP application that I'm using this model for depends on like how good my training data was. Because based on that training data, I'll get some embeddings, and those embeddings will depend on this training process. So that explains that we need to do something about it. And so, as I said, there are two techniques. The first one is this subsampling. Here. Okay, so why did it stop working again? Okay, so one is this subsampling and the other one is this negative sampling. And what happens in the subsampling is that we tweak the training set in such a way that we discard certain words. So basically based on the frequency of those words. And I don't know if you've like looked at any NLP application, there are these stop words like the, and, on, off, and things that are not really adding much to the semantics of something. And so it's like, depending on the frequency, we can adjust the input itself, right? So we can adjust the training process. So that's what subsampling does. I'm going to write it down here. It's also like these two techniques are given in the Mikolov paper. So if you go and read, they have all the details, but still I'm going to, so each word will have like in the training set, is discarded based on a probability value. So you create this like you calculate a probability value for a given word. Let's say like this, the word is W, right? And then based on this formula, like this T over F of this, right? You discard the words that have certain like threshold or value for that probability. And so you choose this parameter yourself. So this is like a hyperparameter T. And this is the frequency of that word. And so depending on the frequency of the word, we can decide, let's say like is coming a lot, right? And so I don't want to like keep getting that as an input to my training set, right? Because like what exactly am I adding to that, to the value? Or like 2 is coming a lot. And so I just figured that the probability of finding these is pretty high. And so based on like some formula, like high level, based on some formula, filtering out those words. And so I'm like making my training process a little faster, right? So that's one way. The other way is this negative sampling. And of course, like the way this negative sampling works is that let's say I'm doing that context word application in NLP, right? So let's say I have the sentence, right? Okay, I'm going to use the same sentence. and there is some context, right? And then there is a word. I have, let's say, an input sentence or some input data text or something, right? And so based on that, I'm like doing this. So let's say the context is again hot, and based on my input, whatever that was, the word that's like very closely related to hot was coffee, right? And so what I'm going to do is I'm going to create this feature target, and I'm going to say that this is the correct one based on my input. Like hot is like I'm explicitly creating this, right? So I'm saying hot is related to coffee, and so that's one. And then what I'm going to do is I'll keep this context and pick randomly some other words, right? So let's say from the dictionary, let's say I pick apple, and from the context of my input, I say that this is not the right one, right? And so basically the word negative sampling comes from the fact that I pick up certain like negative examples that were not correct, right? So I'm going to pick like hot, and I'm picking them randomly. But let's say like cup comes up, right? And from the context of my input, these were not related, but like, yeah, sometimes it is related. So I'm still going to give it a 0, right? So obviously explicitly I'm doing some kind of like tweaking in my data so that I can like resort to some like some updated type of my neural network. So what I'm going to do here is that, of course, I'll have like everything similar to what we did in my original Skipgram model, except that in like if you think about it, the problem that I will be solving is that what is the probability of getting a y, right? Given these context and like this target words, right? So given these words, given the relationship between context and like what is the probability of getting a 1? Okay, so you have seen this kind of a problem before in logistic regression type problems, right? So what exactly is happening is that you will have like these embeddings for like, let's say embedding for the word hot, right? And then you pass it through the hidden layer. And then finally in the softmax layer that you have at the output, right? If you think about it, I'm solving this problem, meaning that for every output, I'm looking for a 0 or a 1, because now my data has changed to this. So basically I'll have, so the output layer, the softmax layer, if you remember from here, let me quickly show you. I think I forgot to mention that here. So the output layer, so if the input is size 10,000, right, the output will also be size 10,000, because for every word in a Skipgram model, I have some probability associated with it, right? That's there. And so that's exactly what I'm trying to do here. So the output that's 10,000, right? Instead of like thinking of that as a softmax and like all of them related, every 10,000 will have like an output of like from a sigmoid, essentially saying that it's whether it's a 0 or a 1, whether it's a 0 or a 1. So basically you're solving 10,000 logistic regression problems in negative sampling. Thinking about like think about this equation here, right? So I'm trying to find out like what is the probability of getting a 1 given these relationships. Let me go back to the paper that actually talks about this, and then how do I escape? Really? I think it's the yeah, Skipgram model. And then here it talks about negative sampling. So basically, this is the objective function that we are focusing on. So high level, what it's doing is that we are creating these new relationships based on like this is the relationship based on my input. However, these other words that I'm randomly picking up from my dictionary are not related to this word, right? So in every pass, I'm solving these 10,000 logistic regression type problems. And this has shown to like make this Skipgram model faster. Okay, so that's what this paper also talks about. And in addition to that, there is this hierarchical softmax model. So what this does, and again, I don't want you to like get into the details of the math, but here what we do is like we get those 10,000 outputs from the softmax, right? So Obviously, all of them are not equally important. Some of them are like very low probability values, right? So if you think about it, we can do some kind of a binary tree type structure wherein we can find the paths to only the words that are very closely related to this context word. So that's exactly what's done in hierarchical softmax. You will get the output of the softmax, but the good thing is that you can create relationship between the high probability words only. And so when you like generate the loss, we only have the high probability values there. That's what, again, no need to go into the like graded math of this hierarchical softmax, as long as you understand the high level, like what's happening in negative sampling, in subsampling, and in hierarchical softmax. So these are 3 ways. Yes. Yes, please. I'm like literally shouting and yeah, this is better. Okay, much better. Yeah, I was feeling the strain in my like throat. I'm like, based on that input, my output is yeah, but yeah, regardless, going back to this Mikolov paper, please go and read it. It's a very important, like a groundbreaking type of paper in NLP. And of course, it talks about the Skipgram model in detail and how can we improve the Skipgram model better. So that's that. And let me see if I've missed anything before we move on to other things. Skipgrams, yeah. Okay, and again, the good news is that implementing all of these are pretty straightforward in TensorFlow. In fact, I've provided link to like Word2Vec in TensorFlow. There's this notebook that's already provided by TensorFlow. I didn't do anything there. So you can like quickly read because it talks about like how can you implement this and how can you use it to like suit your model and your problem that you're trying to solve. Okay, so having said that, going back to the lecture slides, I have some information, and again, I've extracted that information from the paper itself. What is this continuous bag of words model doing, and how is it like different from the skipgrams? And as I said, the only difference here is that, again, we are trying to learn embeddings, but the difference is in the problem that I'm trying to solve. I'm just like trying to predict one word given the context. In the skipgrams, given a context, I'm trying to predict like all related words. So this is what this section talks about. Okay, so okay, another like completely different word embedding technique is the glove technique. And I decided to introduce this because you might come across this as well. This was introduced by Stanford, came after Word2Vec was there. And what they saw was like there was this issue with Word2Vec type embeddings is that sometimes like in a sentence, it's not just enough to just like look at the text and see how like certain words are associated with one another, but rather we can look at the frequency of two words occurring together, right? So if you have some way of like finding out that these two pairs of words are always together, or this particular word appears with these set of words, so then that gives it another, so the frequency of like that word appearing with certain other set of words is important. And that is what has been incorporated in the glove model. So again, this is anyways like a neural network that is learning from the input data. But the way it's doing that is by calculating this co-occurrence matrix. So we'll have a co-occurrence matrix for every pair of words. And then based on that information, I'm going to generate my model and I'm going to generate my embeddings. Again, I don't want to take the credit for glove, so I have provided the actual original paper, and I would definitely want to go over that because it's an important, and of course, Word2Vec is more popular and it's improving continuously, but glove is also another important. I just don't understand why it won't let me. Okay, good. I think it's paper 4, but yes. So glove is for global vectors for word representation. So if you just go inside this paper, and as I said, it works on some matrix factorization methods, but regardless, yeah, so here it's actually showing you what this does. So there is this like probability of getting a value given certain other word. And the way they actually generate is that they look at the co-occurrence probabilities of every pair of words. And so you'll have that matrix generated for like every pair of words, and you want to pick that value of the co-occurrence matrix, which is based on the frequency of that word appearing with those other words. So this is what this is actually telling us. And one more thing about this, the objective function that they are trying to, like the cost function in the model is slightly tweaked as well. And so of course, like the rest of the stuff stays the same. Like in our Skipgram model, we have the standard log loss function. This is slightly different in the sense that you have like this f function, which is nothing but a frequency of like, what is the frequency of getting the word I given j? That's how they are like getting this xij. So that has been added, and because you have this like log value, and there can be like log 0 here, which is like an indefined value. So that's why they have like this value multiplied to this entire like this squared value, so that like you can come down to 0 if you multiply it by that. So that's the convention they're using. But the idea stays the same, that you're trying to find the frequency of like word I given j. Like what is the frequency of this word I given the word j? Like how many times does this appear in the entire text with this word? And so if it does, then there is some association, some relationship between them. So that's the glove model. Again, you can implement it. In fact, you can just like go and Google this, and it'll take you to the original website, Stanford website, where you can just download it and like import and use it if you're interested in like using this model. All right. So 2 different word embeddings we looked at, and I would say the most common one is Word2Vec. So as long as you understand that and the Skipgram model, you're ready to work on any NLP application. Okay, so as far as the applications are concerned, right? And like that goes back to your question earlier, right? Like I'm tempted to again like take some text and learn word embeddings from them, and for like experiment's sake, you can go ahead and do that. But the issue is that you need a lot of data to get really good word embeddings. And that's why this is a challenging problem, because we have sparsity of training data. That means we don't have enough training data. And the way like Word2Vec has been created is that they have used like from different Google sources, they have created like this huge chunk of training data from different sources, and they've created these embeddings, right? So, and then there are a large number of trainable parameters, as you just saw, although it's not a deep network, but it's a wide network. And so it may take a very long time to learn. And so for these reasons, learning word embeddings from scratch is no more the case, and we don't usually do that. And that's why we just like use the existing word embeddings and then go from there. At least they give us a good starting point. But maybe then you can decide to fit another neural network over these word embeddings. That's totally up to you. Okay. All right. So one very well-known application in NLP is the sentiment analysis, right? And the way we can do sentiment analysis using these embeddings. Was that sound from outside? Okay. Okay, so if you remember like how the sentiment analysis is done, is that we are trying to predict like a slide here. Okay, so in sentiment analysis, we are trying to predict a binary outcome given some input, right? Because like you're given some text and you're trying to predict whether it's positive or negative. That's how sentiment analysis works. So how can we use like these embeddings and do sentiment analysis? Well, if I have, let's say, some review for a restaurant, let's say, right? And I'm maybe trying to predict like the number of stars that this review would amount to, right? And so for that, what I can do is like, let's say I have X. So maybe the first one was like the food was excellent. And then you have, let's say 5 stars, right? The food was not good. And so let's say I have like this label data and so on, right? And using the word embeddings, so obviously I'll have some like word embeddings for these, right? I can utilize them to maybe pass it through some existing softmax or something and get the probability values, right? That is like one way of thinking about it. For example, I can have like let's say I'm taking food as the one hot encoding for food was this. And then I also have the embedding for food, right? And then I have the embedding for excellent. And using all these embeddings, right? Embedding for good, I can have the average. So usually this is how we do sentiment analysis using these embeddings. So I already have the embeddings. Maybe I can get the average, or maybe I want to pass it through some sigmoid to get the probability of like how high or low this is. Or maybe I want to do a softmax because softmax will help me get the exact ratings of like 5, 4, and so on. Right? The issue, however, and as always, sometimes can be that these embeddings, of course, are taking care of like the relationship between different words. But sometimes the way the words are phrased in these type of problems can create issues. And so one way out is that if there was like some relationship, like the way these words appear was like, let's say the review was lacking a good service, good food, right? And we just said that we'll capture the embeddings of all these words, right? And I'm going to average them and get the output. Now, if you think about this sentence, like lacking good service, good food, right? I have lots of good here. And so most likely the average or the probability of like the outcome of softmax is going to be high for this one, right? And so for certain situations, specifically for sentiment analysis, what we do is we use these inputs, these embeddings, and use them as inputs to an RNN. Because remember, RNN was maintaining that relationship in the context. So sometimes that is done as well, especially for words like sentences like these. When you have like lots of positive words, and so the embeddings would be, the way we've learned these embeddings is usually that good is close to something like really positive, right? And that's why like if we use the average kind of thing for all these embeddings, I'm going to get like this is a positive review, but actually it's not. So mostly for sentiment analysis, what I would do is, and I think I'm out of slides, I'll add. Is that I'll get the embedding for, let's say, food, and whatever the sentence is, food was not good, was or lacking something, whatever it was, but I'm just like trying to show you what's going on, right? So I'm going to take the embeddings of each of these here and remember what was happening in an RNN. So I'll also have like some relationship between these words as well. So that is another very common way of like using these embeddings. Instead of using the one hot encoded vectors, I'm using the embeddings that were already learned from some other data. But now because like I know that this application, the sentiment analysis can have some relationship amongst them as well, right? Which most likely my embeddings have captured, but this is going to give me a better outcome because remember like what we said when we were doing an average. There's more good words, meaning I'm going to get a good review, right? So usually this is how this is done, that you will have like the first hidden layer, second, 3, and so on, right? And then eventually you will like maybe have a softmax and get the output. So this was like many to one RNN. Like we saw that there are many different variations of RNN. So this is like many to one because I have like many inputs, like all the word embeddings, and then eventually I have like one output, which is maybe a softmax, maybe some probability value. I don't know, whatever the problem is. Right? So this is one way of using these embeddings. Most likely you're going to pick up the Word2Vec. You will have like certain new input, but that new input will have some word representations. But now you know that there is like this added relationship between the words in my new text. And so I don't want to take chances and write. And so I will just input that into a new neural network. That's one. And of course, like the one thing that I want to remind you is that remember the LSTM and GRUs, one very common application is that instead of like each of these would be an LSTM, maybe, right? Yeah, you had a question. Okay.
Experience about like the loss function, and it's only on
Yes, yes, yes. That's a good one. So this is, I will have only one loss as opposed to like the multiple ones that we saw in RNN. And then the back propagation is going to be through this. Yeah. Okay, so that's that. One thing which is not like directly related to today's lecture, but I still wanted, and I think it's an important like aspect of any neural network, and specifically these language models, is that we have trained them on some input data, on some input language text, right? And then that input language or text or like whatever sources we are gathering all our information from can have certain biases. For example, like it has been found in Word2Vec, and it's a known issue with Word2Vec, is that if you're trying to do some kind of prediction, or if you're trying to find the relationship between, let's say, man and doctor, usually what comes out for a woman in a Word2Vec is like a housewife, right? So this kind of like a bias, a gender bias, is introduced because obviously that's how we trained our like model from some input, right? And so this bias is already introduced in Word2Vec. And this was rightly pointed out in this paper. And this is an important like research problem as well. So if like you're interested at all, like how to deal with these, bias in word embeddings. This is a known issue, and I think this wasn't a very old paper, 2016. This paper was in 2016. And so what they like demonstrated is that in Word2Vec, there is this like high level of bias, gender bias specifically, that exists. And obviously we need to do something about it. For example, here you can see what all like, yeah, so here they're just showing some results of like how this bias comes out in Word2Vec based on like a lot of like gender related words. So what they propose in this, like they propose a new algorithm, and they say that this is like, for example, this is a good example. So they said like man minus woman is what they're getting is like a computer programmer. So man is for a computer programmer, and then woman comes out to be a homemaker. So homemaker comes out as like the nearest one, which is like sad, I would say, right? But yeah, this is what it is, because like your model is as good as your data, right? And the thing is that it's so inherent in our language, it's so inherent in all our sources, that there is little we can do as far as like the current state of skipgrams is concerned, right? But then they say that they can do something about it in terms of like tweaking this model and creating certain new models. So that's what this particular I would say paper talks about, and I focus on, and they're like, these are very simple tweaks that they do de-biasing these algorithms. So for example, here, like what they're doing is they're projecting, so like selected words projected along two axes, and along like one of the axes, there's like the difference, so they find the difference between like he and she, for example, woman and man, right? And so then you can have like this new axis, which can be like, um, which can get rid of like these differences, right? So first, like identify the bias direction. So the bias direction most likely is the difference between he or she, man or woman, right? So if we can get rid of that and just like neutralize that, so obviously we have to use techniques like PCA and other things. And then in this like new space, we do our predictions. Now, the issue with this technique is going to be that there are certain words that need that gender like identity. For example, like boy versus girl or something like that, right? So in addition to doing this like de-biasing, and here they actually talk about that, they have this additional step of like equalizing those words that actually need some kind of gender identification. For example, like a profession does not need a gender identification, right? So just de-bias that. And then like certain words do need that identification. And like high level thinking about it is like, let's say there's like a babysitter word, and then the distance of babysitter from grandfather versus grandmother, right? And so usually it was found in Word2Vec space that grandmother was closer to the babysitter, and so most likely it's going to come up as like babysitter. So explicitly, what they do is they de-bias that grandmother by like adding certain distance to that word such that they are equal. So like grandmother and grandfather are equidistant from babysitter. So like that. Again, like this is a very good addition to de-biasing algorithms. It's a pretty simple, like straightforward one, wherein all you're doing high level is that you're just like creating distances between words, but then you have to make sure that you're not creating distance between the actual gender specific. This is a very active area of research where we are trying to come up with more like bias-free algorithms in AI. And NLP models are more prone to it, given that they're based on our language, right? So please go and read this paper, like very important. And this gives you the details of like how they are de-biasing. Specifically, there are 3 steps, right? So identify gender subspace, get rid of that distance that you have, right? And then neutralize and equalize. So yeah, reading through this would make a lot of sense. Yeah, I think I talked about this example. All right, one last thing before we end today's lecture is this like notebook. So if at all you're planning to work on any NLP application, this is provided by TensorFlow. So you can just like go and quickly read through like what Word2Vec is. And they have a proper implementation of Skipgram using negative sampling. So negative sampling is the algorithm that makes it faster. And yeah, they give a good example of how this is done. This is the objective function that we are trying to, this is the final loss, right? And this is the softmax output. And more importantly, we've already discussed all this, so I'm not worried about that. More importantly, they tell you about like the setup and how to like train your network using Word2Vec. So please like take some time playing with it, just like changing a few things and seeing how you can use it for your own model. But yeah, so let me go back. Yeah, this word is going to come up again just before we end this lecture. Transfer learning and transfer embeddings, as I said, and I've repeated that earlier. And this was like one of our first exposure to transfer learning in some sense, because like somebody already has that network existing with some learned values, and we can build our network on that. Okay. So that's all I have for today's lecture. Yep. And on Friday, we are going to continue talking a little bit more about NLP because there are certain things that still remain. So yeah, that's all. If there are any questions, you can ask. Otherwise, that's it. Thank you so much.